name is Alexander Dunn, and I am sitting in beautiful Littleton, Colorado today. On behalf of my co-authors, Dan Kennedy Jr. and Danielle Cleveland, I am pleased to present our paper, Enabling Hybrid Architectures and Mesh Network Topologies to Support the Global Multi-Domain Community. First, we'd like to thank the AIAA USU SmallSat Organizing Committee for staying committed and agile through this whole process. We would also like to extend our well wishes to the global SmallSat community during these trying times. This presentation comes a little bittersweet, as we are grateful to have the access to the technology that allows for us to keep the continuity of the SmallSat conference, but we are going to miss the face-to-face interactions with all of our friends. We're very much looking forward to SmallSat 2021 being back in Logan, Utah next year. When we first started working hybrid architectures and mesh networks, this pandemic wasn't even on our radar. But perhaps this pandemic has highlighted the need for instantaneous access to data and the interconnecting of platforms without complications. The emerging global demands have had two major anchors: better data products and reduced data latency. These anchors can only be achieved through interoperability between the domains: space, cyber, air, maritime, and land. Up to this point, and even now, domain operations are much closer to stovepipes rather than fully integrated multi-domain operations. For sure, there have been some examples of cross-domain functionality, but unfortunately, most of these are being implemented via brute force and one-off or specialized cases. A fully realized global MDO will rely on space hybrid architectures and mesh network topologies for seamless transitions. So, the objective of the authors was to outline the strategic path and advantages of utilizing SmallSats and their relevant technology to fully realize multi-node, disparate architectures and networks to support future multi-domain systems. To address this, our paper first briefly discusses the history of SmallSats and how we got to today's environment and what challenges are still present. Then, we look at the emerging capabilities and what technology enablers are driving hybrid architectures and mesh network topologies. We'll look at what multi-domain operations may look like in the future, and we'll discuss who the early adopters of hybrid architectures are. SmallSats have come a long way since Sputnik. Most of the progress has been driven by strong advances in onboard computing, as well as more affordable access to space through launch capabilities like ESPA. Standards, too, have played an important role. The CubeSat standards in 1999 kicked off the first SmallSat revolution. SmallSats began to excel in the faster and cheaper categories. However, SmallSats still weren't considered the better solution in the early 2000s or even the 2010s. And this is due to some inhibiting challenges. We wanted to highlight some of the most prominent challenges in SmallSat utilization that we've observed over the last decade. Challenges that have been prohibiting SmallSats from progressing out of demonstration and experimentation categories and into fully operational solutions. To achieve the same functionality as large capital asset satellites, SmallSats must be used in multiple nodes, such as constellations and clusters. And even though the CubeSat standards have helped to streamline the production of CubeSats, a standardized form factor for multi-mission microsats, such as 50 to 200 kilogram range, doesn't necessarily exist yet. Streamlining the design, assembly, integration, and test has not yet been fully realized in order to support these large constellations. Another large inhibitor has been the lack of commonly accepted standards, which prohibits continuity among programs and prohibits interoperability between disparate systems or organizations. This is what leads to those stovepipe space architectures. The graphic here is depicting how SmallSats have typically been implemented for most of the last decade. Again, the stovepipe nature is prevailing, and strict firewalls are being implemented to prevent data sharing between two companies. Finally, most SmallSat integration is done via ground activities. Two factors drive today's integration activities via ground: cost and capacity of onboard versus ground processing resources, and rigid architectures, which prohibit easily updated comms path and computational algorithm updates for onboard spacecraft. However, the global SmallSat industry has seen a second revolution over the last few years, which seek to solve many of these challenges. You all have probably heard this referred to as new space. The new space market has indeed exploded in recent years. great resource for the state of the new space market is the global ranking reports released each year by new space people. Looking at some of the highlights here, you can see the international market shares having a positive trend, trending upward. We believe this will continue as technology continues to advance, which opens up space markets and collaboration worldwide. So how is the new space revolution molding the small sat landscape? Looking at this graph, you can see the beginning of the last decade, small sats were most used for technology development and not operations. That began to change in the middle of the decade, where you can see remote sensing making significant jumps in small sat utilization. There have been and continue to be pushes for remote sensing constellations like SAR and hyperspectral imaging. The transition from technology development to remote sensing signified the desire and market demand for better data products, one of the key driving factors for multi-domain operations. Continuing through this timeline, you can see the increase in communications for small sat utilization. This probably comes as no surprise to anyone here, as there are heavily publicized constellations doing just that. This comms push, however, is the answer to the reduced data latency demand we also discussed earlier. Together, the remote sensing and communication utilizations is establishing the infrastructure for our space hybrid architectures, mesh networks, and multi-domain operations of the future. Recently, there have been some heavy investment in some game-changing concepts such as Internet of Things, on-demand remote sensing, and space dial tone. Many of these are quickly transitioning from ideas and concepts to real operational technologies and services. Much of the progress made on these emerging concepts is addressing the most notable inhibitors in small sat utilization for these complex next-generation multi-domain operation solutions. Most notably is that of modular open system architectures, or MOSA, which are now beginning to be embraced and implemented globally. Embracing MOSA and the new space approach is changing the landscape for future space architectures. We are abandoning the stovepipe approach and are integrating systems and leveraging collaboration across the industry. This is the key implementation of mesh networks and space hybrid architectures. Not only will multiple architectures integrate in hybrid architectures, but solution costs will be driven down through streamlined manufacturing and multi-node acquisition within the mesh networks. Some in the industry believe that in the future, data captured from these systems will not be owned, but rather shared. Whether or not this proves to be true or false, or more likely somewhere in between, is still to be determined. However, this sentiment is the theme of the disruption of the new space approach. Moving on to technology enablers, we begin with network and messaging segment. Here, modular open system architectures, or MOSA, is a prominent contributor. MOSA enhances competition, facilitates technology refresh, incorporates innovation, drives down costs, and improves interoperability. But instead of needing a single adopted standard to achieve this, the solution will be to translate between messaging standards through what we call meshes agnostic physical protocol bridges. These enable interoperability between disparate systems, driving standards, and internet-based control definitions. Bridges also accept messages from an incoming source and transforms them into a format that an outgoing receiver can interpret. This allows for the integration of subsystems and components into a MOSA system, but also allows the integration of nodes within disparate architectures, thus creating the hybrid architecture approach. Continuing with our technology enablers, we look at those technologies supporting communications. In the same concept as MOSA, a key tenet of true hybrid architectures and mesh networks is the standardization of electronic data sheets, or EDSs. Electronic data sheets serve as the foundational backbone of interoperability by enabling a given architecture to integrate with a previously unknown or undefined architecture, thus creating the hybrid architectures. As these large architectures with multiple nodes and satellites continue to grow, a well-coordinated dynamic relative telemetry calculator will be required to do comms link analysis. This will feed into predictive metrics for tasking commands as well. Digital twins are commonly referred to as fault management systems. This is still true. However, digital twins will also be used for fast-forward predictive tasking. Digital twin networks will allow operation engineers to understand the proliferating effects of an action before executing that action. Finally, our satellite development operations enablers. Assembly line production is also now becoming more mainline in our industry. Again, this is aided by the embracement of MOSA and the ability to quickly plug and play components from different manufacturers into configuration and still ensuring that that assembly line keeps moving forward. Space hybrid architectures and mesh network topologies, especially for multi-domain operations, are going to be very complex systems. And it's going to be too much for our current human-in-the-loop operations management approach. Machine learning and artificial intelligence will be implemented in order to conduct data processing, but also, to some degree, some decision-making in the information decision space of MDO. Finally, the new space environment is also now operating what we call integrated design environments. Technology today enables different teams to collaborate on a single mission distributed across multiple continents. Again, a critical aspect for hybrid architectures in space and an enabler for multi-domain operations. Once these technologies are realized and space hybrid architectures and mesh networks are operational, our new global multi-domain community will have a much different synergy. We imagine the two-dimensional visualization will look something like the diagram shown below. The domains are no longer stovepiped, and we can seamlessly interoperate with each other. Additionally, the functions within each domain, for example, the Department of Defense or the Intel community, commercial assets, and foreign allied coalition assets, can also operate seamlessly within the MDO architecture. This will help ensure the best data products are available. Assisted by AI and machine learning, the data latency and decision points will also be accessed. And this will ensure that reduced data latency is also achieved. Once fully integrated, these multi-domain systems will be seamless and very effective. Today, there are a few early adopters, mostly on the US government side. Most of us are familiar with DARPA's Blackjack program, which will help improve the SMC's casino instantiation of that. The Space Development Agency is also implementing a multi-layered approach to hybrid architectures in support of the Space Force. And AFRL conducts hybrid architectures and mesh network experiments through a multinational exercise, co-aligning with the Naval RIMPAC exercises. This exercise takes assets from Department of Defense, commercial, and foreign allies to conduct these experiments. These programs will be the first major milestones in implementing a truly global multi-domain community. We are very excited to see what lessons learned can be taken from these trailblazing programs and how quickly we can implement true multi-domain operations using hybrid architectures and mesh network topologies. And with that, I would like to again thank the SmallSat Conference and organizing committee, and thank you all for listening to our presentation. And again, we hope to see you all soon.